Good morning, and thank you very much for the invitation to give this talk. I am very excited to present our new Superconducting Quantum Materials and Systems Center. This is one of the 5 new Department of Energy National Quantum Initiative Research Centers. I'm Anna Grassellino. I'm the new SQMS Center Director. So let me start by introducing what is the framework for these national quantum centers. The US National Quantum Initiative in 2019, Congress mandated the creation of 5 Department of Energy National Quantum Centers. This is about $625 million over 5 years to develop quantum computers, quantum sensors, and quantum communications. The goal is really to bring transformational advances in quantum science and in quantum technology to create a quantum economy. And really one of the important aspects here is that these centers are led by Department of Energy national laboratories, but they really bring together a multidisciplinary collaboration that encompasses the world of the national labs, of academia, and of industry. In August, Fermilab was notified that it was a long and difficult competition for several months. We actually first wrote a proposal and then we were under review. But then finally in August 2020, we were notified that Fermilab was one of the 5 national labs to lead a DOE National Quantum Center. Our center, SQMS, really brings together the power of DOE national laboratories together with industry, academia, and other federal entities to achieve transformational advances in quantum technology for computing and sensing. Fermilab is the lead institution, but you can see here the logos of the other partner institutions. We are about 20 partner institutions. Rigetti Computing is our primary industry partner. Ames National Laboratory is one of our core partners, and along with Northwestern University and NASA Ames Research Center. We also have several other universities, NIST, the Italy participation with the Italian Institute for Nuclear Physics, and also industry strong presence with, for example, Goldman Sachs or Lockheed Martin or Janus. This is how we are geographically distributed. So it's a national center. So obviously we span from east to west coast. And as I said, we also have one international partner, which is the INFN. We really bring together substantial and leverage substantial investments in facilities that were developed by the Department of Energy, but also in other programs. So larger than $500 million in several facilities that go from superconducting qubits and superconducting cavities development to several other facilities. We have more than 80 PIs. And here in numbers, you can see some other important things like several government laboratories, several universities, quantum foundries, and so on. And we have already up to 200 collaborators. What we really bring together is key expertise. And again, this is what the emphasis is in these national quantum centers, is to bring together the multidisciplinary aspect. So all the different experts and facilities from many areas that are key for the advancement of these complex quantum technologies. So of course, Fermilab brings to the table one important technology, which is radio frequency superconductivity, which we have used for many years, and we have been leaders worldwide for SRF in the world of accelerators. But this is a key technology that actually will be instrumental for the construction of a quantum computer based on superconducting 3D architectures. We bring material science experts from Ames National Lab and from Northwestern University and many other places. We bring also substantial expertise in cryogenics from Fermilab, but also from other places, controls and electronics, superconducting qubits, scale-up and integration, computational science, particle physics, condensed matter physics, and of course industry for looking at industry use cases, for example, of the quantum computer prototypes that we will be developing. As I mentioned, our center really leverages unique national facilities. So from World Unique, here you can see some of the pictures really kind of at a glance trying to show the breadth and of the facilities that we bring together, from World Unique superconducting 2D and 3D foundries to material science and superconducting characterization tools to millikelvin test beds, that all will be taken actually even beyond the state of the art. So we not only bring together these unique places and facilities and experts, but also at the same time, we will make some focus investment to bring these facilities beyond the state of the art to be even more targeted to the problem that we are trying to address. Here I wanted to actually mention some of the examples of the Fermilab facilities, and really, as I mentioned before, we have very big strength in superconducting RF cavities that you see pictured here. Those are 3D structures that sustain electromagnetic field inside up to several million volts for accelerator purposes. But in this case, for quantum, we will be using them in a very different regime, which means containing inside very few photons. And so we bring this structure to the opposite regimes in dilution at millikelvin temperatures and dialing down the power to really be quantum objects. And they could become very powerful processors. So from dilution refrigerators to full multi-qubit measurement capabilities to new material deposition furnaces, plasma system, electropolishing system, we really Fermilab contributes very strongly on the technology side, but of course also on the application side in terms of what are the science applications that we will enable with this quantum computing building blocks and also quantum sensing building blocks. Here's an example of other facilities from the partners, and this is one of our primary partners is Rigetti Computing in California, and this is one of their clean rooms where they produce 2D qubits, transmon qubits, and then from there they integrate into actual quantum processors. The center is organized in two trusts, actually with 4 focus areas. So we have quantum technology as enabling trust and the quantum science as the application trust. In quantum technology, we work on materials for 2D and 3D quantum devices and on devices integration, prototypes, and quantum processors. So really here, the focus is on understanding and improving the materials that are utilized in these superconducting qubit platforms to push to the next generation of performance. And at the same time, from the single building block, single qubit performance, to integrate into a more processor unit, so a more complex scaled-up system, even up to a quantum computer prototype, and we'll be talking a little bit more in detail about that. In the application trust quantum science, we actually have 2 focus areas, quantum physics and sensing, and algorithm simulations and benchmarking. So the prototypes that will be developed in the quantum technology trust in terms of quantum computers, for example, or devices, will be employed for simulations in the science world, but also as sensors, potential sensors to discover, for example, new particles. In the technology goals, so what are the main goals of the center? So as I mentioned, we will take this SRF cavities, so these radio frequency superconductivity cavities that at Fermilab we have mastered to be the world's longest coherence SRF cavities in the world, together with the Rigetti transmon qubits, will be for the first time integrated to make the best possible quantum processor building blocks. So this could potentially lead to transformational advances in QIS building blocks. We are launching an unprecedented scale material science investigation for decoherence causing defects, understanding, and mitigation. So we are basically going to do a unique fast turnaround study of 2D transmon qubits and all its materials and subsystems to correlate device performance with the actual nanostructure of the device. And this is really thanks to combining together unique industry manufacturing capabilities with the best material science facilities and superconductivity facilities and experts. We will be studying the parts of the actual measured cavities and qubits, so we'll be giving a glance of this type of approach and methodologies that we are using. We want to create national and international platforms for cross-checked measurements and qubit performance benchmarking, and we want to scale up to quantum computer prototypes. So the focus, as I mentioned already, of SQMS is on superconducting qubit platforms, uniquely on this type of qubit platforms. This is because we really are expert in that, and because we possess in particular, the 3D superconducting qubit platform technology advantage at Fermilab. So what do we mean by superconducting qubits? They always have two components. One is what we call a transmon qubit, which is an LC circuit with a Josephson junction, and then a resonator. The resonator cavities could be 2D, meaning that they reside with the transmon qubit on a chip. They look like that. Or they can be 3D, meaning that they are three-dimensional resonators, cavities, inside which we would then integrate this 2D chip, the 2D transmon qubit. And they may look like this, or they may look like this, for example. So this is an example of a Fermilab SRF resonator. So the idea here is that SQMS, by improving the coherence, and by coherence means how long do these devices are able to maintain to sustain quantum states. The coherence, the lifetime of these quantum states in these devices, we aim at improving dramatically the coherence of these devices of both components, of the transmon qubit and of the resonator cavity, and of the system combined, and therefore bringing transformational advances in the fundamental QIS building blocks. And potentially these can lead to quantum computing scalability and quantum sensing potential for discovery. In SRF cavities, so Fermilab resonators in the quantum regime for 3D resonators. So what is our strength? We have demonstrated that these cavities are the highest coherence quantum resonator ever demonstrated in the superconducting world. We demonstrated up to 2 seconds of lifetime. So here in this plot we can see actually the paper where we published recently these results. So the QIS state-of-the-art for 3D superconducting architecture has demonstrated milliseconds, but with our cavities actually we originally managed already to kind of more than triple that, but then with some further research on surface treatments that will eliminate the surface oxides where the so-called two-level system losses reside, we were actually able to demonstrate a jump in a factor of more than 200 in the coherence time, so in the photon lifetime inside these devices. So this is here shown at millikelvin temperature and very low photon count, so really in the TLS-dominated regime of SRF cavities. So how did we achieve these results? These results were achieved with a powerful methodology of combining device fabrication and measurement together with the material analysis. So you can see here the full-scale device, and then here you can see a zoom in of the inner surface at the nanostructure, showing the first 5 nanometers of the surface being a native niobium oxide on top of niobium, very high purity niobium. And so this niobium oxide, we did several studies and demonstrated that this is where the losses in the quantum regime would reside, and by dissolving this oxide with some special treatment, in situ heat treatment, we actually managed to obtain this very interesting results of 2 seconds of lifetime. And so again, this was by combining, for example, secondary ion mass spectroscopy measurements together with the device testing. This is really a unique advantage starting point, as we have the best 3D structure ever demonstrated. And next, we want to actually integrate them with an element that will give the nonlinearity to the resonator, which is the transmon qubit. The transmon qubits will be coming from Rigetti. Rigetti Computing produces transmon qubits. They are at the forefront of coherence. You can see here from one of their papers, there is some spread in performance, but their best qubits have reached even up to 400 microseconds in performance. So we would be able to cherry pick the best qubits to be integrated with our cavities, but at the same time, we also want to help advance the 2D architecture. And so what I was mentioning before is that one of the studies that we will be doing is really, again, taking devices from Rigetti, 2D transmon qubits that have this spread in performance, and then addressing, for example, the problem of spread. Why some perform a few microseconds and some are as high as several hundreds of microseconds, and do extensive material studies employing all the state-of-the-art material science tools to look at the substrate, the interfaces, the different materials, and really correlate performance, like good lifetime, bad lifetime, with what we find at the level of nanostructure. And then inform, based on the knowledge that we acquire, inform the reprocessing, so the processing the Rigetti has for producing these devices to produce new qubits and so on. So it's like a feedback loop type of work. We also want to launch the first systematic cross-institutional benchmarking study of qubit performance. This is again to really develop a fundamental understanding at the device level of why these qubits perform, for example, differently under different cool-down conditions, under different, for example, magnetic field conditions. And so really get to the point of highlighting all the different factors that really come into play and develop a full understanding of the physics of these devices. And so we will be exchanging well-characterized devices like qubits and cavities and passing them around in a full systematic studies under as identical as possible conditions at Fermilab, at Dilution fridges at Rigetti, at Colorado and NIST, and also at INFN Gran Sasso underground to study really the effect of these devices above ground and underground, and at Northwestern. This is the slide that actually explains a little more in detail the first-time integration of SRF cavities with Rigetti qubits. So as I mentioned, for the first time, we integrate qubits that you can see on this rod inside SRF cavities. And we have already successfully proven that at first shot, by integrating our cavity with the qubits, we have achieved more than 30 milliseconds of lifetime. And this is without the heat treatment that had taken us to the 2 seconds of lifetime on the empty cavity. So as a next step now, we will be actually repeating this heat treatment to really try to demonstrate very long lifetime of the order of seconds on the combined integrated system. One of the goals, ambitious goals of the SQMS Center is not only to stop at the level of the improvement of the single qubit, of the single building block, but it's actually to scale up into a full quantum computer prototype. So this would be the first quantum computer prototype built at Fermilab. And we really, again, want to capitalize on our expertise in SRF and in cryogenics. And so here in this slide, you see 2 things. First of all, in this rendering, we show a very large dilution fridge, substantially larger than the largest available commercial unit. So we are going to build a custom dilution refrigerator of the order of larger than 2 meters in diameter and several meters in height. Again, capitalizing on our expertise and facilities in cryogenics that we have at the lab. So this will be really the largest unit ever built in terms of being able to host a very large number of qubits inside. And in this table, we actually outline some of the center quantum computer prototypes that we want to deliver by year 3 and by year 5. And some of the performance of these devices that we aim for. Of course, there are different metrics, but you can see, for example, that by picking some metrics compared to the current leading systems, so we have the potential, if successful, to go many orders of magnitude above. Again, this is thanks to several factors. The fact that we bring the Department of Energy unique expertise and facilities for building large complex SRF and cryogenic systems, plus the industry scale-up capabilities. We also capitalize on this broad multidisciplinary collaboration that covers all key aspects of the work in so-called co-design. From Rigetti routine experience in building quantum computers, full stack, to, for example, some collaborators like NASA, Northwestern, and others in QIS theory and applications, and the Department of Energy devices integration, and so on. So in a nutshell, I just want to say that really modern accelerators, which are our bread and butter, Fermilab, are a little bit like quantum computers. They are large and complex, high coherence, so high quality factor, 3D superconducting microwave systems. And our lab, DOE lab expertise and facilities can be critical for success in scale-up of 3D QAS technologies. So here's some of the actual technical areas that really overlap with between accelerators and quantum, so such as vacuum systems, superconducting materials, microwave superconducting devices, cryogenics, controls, magnetic shielding, and so on. And in some pictures here, we're showing what we have done recently is building, for example, an accelerator at Stanford that is a kilometer long of SRF cavities that have performed at larger than 310 to 10 at 2 Kelvin. So we really have mastered scale up and building a large SRF system with very high coherence time. And we want to kind of repeat this in a different regime, which is in the quantum regime. What is the advantage of that? I've been talking about this approach of 3D quantum architecture. What is the advantage? What are the unique benefits? Again, in this approach, the cavity, so where we, for example, encode really the states, the quantum states, not in the transmon qubit, but really in the states of the cavity. So the transmon qubit really serves as a nonlinear element, and the cavity itself becomes the main player where we utilize the different modes of the cavities to encode the quantum states. So this way we would be taking advantage essentially of the world best coherence. So we will be taking advantage, while the coherence time of the transmon might still be limiting, we would take a full advantage of the coherence time of the actual cavity. Of course, the integration, as I mentioned before, it's still important, meaning can we preserve with the integrated system this very long lifetime. But if we are successful, we can basically with one structure like this obtain something which is more than like 100 plus qubit processor with just one of these structures. So again, long coherence allows going from qubit to QDIT approach. Scalability is one of the potential advantages. With just few input and output lines on this structure, we would have more than 100 qubits. And then it can offer really great advantages for science. For example, building very large CAT states inside the structures will allow to work on quantum science experiments to probe the micro to macro boundary, or also we are looking into utilizing this structure to search for dark matter. So this is our quantum computing roadmap. So what I told you so far is that we try to advance on a quantum computing roadmap towards quantum advantage, shooting on two different fronts. One is improving coherence, so pushing the coherence of transmons, pushing the coherence of the 3D cavities and the integrated system, and also pushing on the system size, pushing on the number of qubits. So this is where the leading systems are, and this is where we think we can go with the 2D and 3D systems that we will be building with SQMS. So potentially entering the quantum advantage era. Of course, to enter the quantum advantage era, technology alone is not sufficient, and that's why SQMS collaboration really brings together a broad collaboration that encompasses from the technology expert to the science user. So, of course, we have our in-house particle physics experts that will be looking at applications for understanding better the world of particles. So, for example, understanding better particle collisions. And here we're giving some examples, and what's shown in this plot here is how we are mapping at the same time compared to the previous plot, the technology plot, we are mapping some of the center goals in year 3 and year 5 in terms of different high energy application or condensed matter application that we think our system may be able to enable. And one of the advantages that the 3D architecture is actually all-to-all connectivity, which could be very well suited to simulate quantum field theories. Another aspect that I want to touch upon is actually that our SQMS collaboration also focuses not only on the computing part, so not only we have this very ambitious goal of building a revolutionary quantum computer Fermilab, but we also want to employ these building blocks, these structures, for actually as sensors, so as quantum sensors. So what does it actually mean? One of the examples is shown here in this figure where we have two SRF cavities. One is in the accelerated regime, so meaning it's powered with a lot of photons inside, like 10 to the 24 photons. Another cavity is actually in the silent quantum regime, so it's a very low field and low temperatures and act as a receiver. So this is an emitter, this is a receiver. This is a light shine through wall experiment for the first time employing SRF cavities, searching for dark sector particles. So in particular, what this experiment is looking for is dark photons, which will be a potential equivalent of the photon in the dark sector. So what does it actually mean? It could be a particle that exists, but it's so weakly interacting with the world that surrounds us that it's elusive and does not interact with matter, and it is very hard to detect it. How can an experiment like this and how can quantum sensing help detecting the presence of a dark photon? So this cavity contains 10 to the 24 photons. These photons remain confined inside the cavities because photons interact with matter and therefore cannot cross the walls. But dark photons don't interact with cavities, with the walls, and can actually escape this cavity. So if dark photons exist, the photon converts into dark photon, escapes these walls, passes through the walls of the receiver cavity, reconverts into photons in this cavity, and this receiver cavity, which is silent and in the quantum regime, actually is able to detect the presence of photons which should not be there. And the only way that these photons could have gotten there would be through this dark photon mediator. So this is one of the examples of how a cavity in the quantum regime can turn into a really quantum sensor, meaning able to detect even single photons. And the single photon presence would be an anomaly indicating potentially under particular conditions such as this particular scheme, potentially indicating the presence of the existence of such a particle as a dark photon. This is just one example, but there could be several schemes that we could put these cavities under a certain presence of magnetic field and, with several modes ignited inside these cavities and so on, that could reveal the presence, for example, dark matter, axions. And so this is summarized in this plot, where our quantum sensor or quantum devices have two, for example, factors that allows us to explore the unknown. One is the coherence again, so how long these devices live, and then another factor is under which magnetic field, for example, they can be subject to. So why the high coherence helps pushing the sensitivity of these experiments, orders and orders of magnitude, because in this particular case, the high quality factor, the high coherence of the emitter cavity allows to generate a lot of photons and therefore a lot of dark photons. At the same time, the high coherence of the receiver structure allows the elusive photon present potentially in the cavity not to be instantaneously absorbed by the cavity, but to actually bounce in the cavity as in a perfect mirror and be therefore detected. And really this is how we will be pushing in our center. We have a coalition of top theorists and experts conjecturing the presence of hidden particles, working together with the technology experts to really devise new schemes and potentially prove experimentally the presence or the absence of this. And this is actually a sensitivity plot showing that we, compared to the existing limits, we can push orders and orders of magnitude. So again, this is just to give an idea that additionally these building blocks that in the quantum regime we are developing for a quantum computer can also be enabling quantum sensors for particle physics application, but potentially also for other applications. As a last, I just want to say that the 5-year vision of our center is to really develop unique quantum foundries and quantum computers and quantum test beds that will enable new science. So here in this schematic, you can see the quantum computers prototypes that we will be developing will be serving, of course, the community of collaborators that SQMS has, but our vision is after the year 5 to actually open up these quantum computers potentially also to external users. Quantum sensors test beds similarly, and materials and qubits characterization test beds, really that could be unique to serve as national quantum facilities to enable new scientific studies. So in conclusion, our SQMS Center is really, we're very excited about this new adventure. It's a unique collaboration gathering multidisciplinary top talent and facilities from the US, but also from Italy, towards very ambitious quantum computing and sensing goals. We will have a very focused mission, which is building together something revolutionary.